Alright, so let's go on with section 8. We're on page 380, and here there are two examples of non-strictly determined games, and I encourage you to read these examples. I think you need to be able to read and understand examples, but the bottom line is that all this verbal description comes up with this matrix representation, and you can verify that this is non-strictly determined. In fact, the diagonal entries are smaller than the corresponding off diagonals, so this is non-strictly determined. And this one also is non-strictly determined. The diagonal entries are larger than the corresponding off diagonals, so this is non-strictly determined. So the point here in this discussion of the game here is that if your opponent can figure out what strategy you're going to use, they can take advantage of you. And if you can figure out what strategy your opponent is going to use, then you can take advantage. In other words, if we have two people play and one person makes his choice first, then the other person can take advantage of that first choice to make a better choice. On the other hand, if the column player plays first, then the row player can take advantage of that knowledge. So what you want to do is have a strategy where the other person doesn't know what you're going to do. There's going to be some randomness or a secret part of your strategy that the other person doesn't know. You're going to choose one strategy some of the time and the other strategy also some of the time. But you have to do it in such a way that the other player doesn't know what you're doing. Okay. And that's what we're going to call a mixed strategy, where you choose one option some of the time, another option some of the time. You choose both options with a certain probability, but you do it in such a way that you don't inform the other player. You spin a spinner, throw a dice, or generate a random number on a computer. And then you come up with a strategy where you won't always win the same, but over the long run, your expected winning, or your winning per gameplay, will be as favorable as possible. Whether you're the row player and you want to maximize the positive, or you're the column player and you want to minimize the positive. So let's see how that works out. First, let's give a formal mathematical definition. By a mixed strategy in a 2x2 game for player R, we shall mean a command of the form play row 1 with probability P1 and play row 2 with probability P2, where we assume P1 is non-negative, P2 is non-negative, and P1 plus P2 equals 1. If you know just a little bit about probabilities, probabilities always have to add up to 1. If you flip a coin that's 50-50, that means probability 1/2 you get a head, 1/2 you get a tail. If you have a dice and you want to either thinking about rolling a 1, you roll a 1 with probability 1/6, and you roll anything other than a 1 with probability 5/6. So if you have two alternatives, then the probabilities need to add up to 1. We can similarly describe a mixed strategy for player C as a command of the form play column 1 with probability Q1 and play column 2 with probability Q2. And here again, the sum of these two probabilities must be equal to 1. So we describe the mixed strategy vector for player R as a row vector, P1, P2, where P1 plus P2 equals 1. And the mixed strategy column for the column player is a column vector, Q1, Q2, sum of Q1 plus Q2 equals 1. Okay, here in the book it gives some examples of strategies. Then there's this discussion of how to actually do a mixed strategy. But I mean, in this age of computers, you can always generate some random number. He talks about spinners and pointers and die and things like that, but we don't really need to think about that. With the computer, we can always generate random numbers, and that's not a problem. All right, so let's generalize this definition not to just 2x2, but to an arbitrary matrix game. Remember, we don't just have to have two strategies for each person. We can have any number of strategies. Well, this generalization is what you would expect. Let G be a m by n matrix with entries Gij, so that's m rows m possible strategies for the row player, n possible strategies for the column player. So our n component row vector P is a mixed strategy vector for player R if it's a probability vector. Now in this case you're going to have non-zero entries, and the entries will all add up to 1, just like in the 2x2 case. Similarly, an n component column vector Q is a mixed strategy vector for C if it's a probability vector. Again, n components for the n possible strategies, or n possible options, and then they have to sum up to 1. Okay? Let V be a number, let E be a m component row vector, all of whose entries are 1, and let F be an n component column vector, all of whose entries are 1. It follows that the vectors V and Vf are, here we go. So this VE and VF is just a convenient way of specifying vectors for which all entries are the same and all entries have the value V. In this case, V is a number or a scalar that multiplies this vector, and this vector has all 1s, so that means that each component of E is multiplied by V, and I get m components, all of which are V. Similar with this column vector, VF, F is a column vector with all 1s. Multiply that by the scalar V, you get a column vector with all V's. Now we define the value of the matrix game matrix game G, and P0 and Q0 are optimal strategies for the players if and only if the following inequalities hold. P0 times G is greater than or equal to VE, and G times Q0 is less than or equal to VF. Now when you say greater than or equal to, you're talking entry by entry. This P0G, this P0 is a vector, it's a row vector. This G is a matrix. The result here is going to be a row vector of the same size of VE. The result here, GQ0, is going to be a column vector of the same size as VF. All right, this has n components, this has n components. Now, why we make this definition may seem a little bit mysterious. I think as we work with these games you'll see, but suffice it to say that this is very similar to the max-min condition and minimax condition that I've been talking about. The max-min condition means that you want to maximize your minimum benefit. The row player wants to maximize minimum benefit, and the column player wants to minimize his maximum loss. This V is kind of like a saddle value. If I put this V in every row, then if I use this strategy P0, then P0G is going to give me the payoff for each possible strategy that the column player uses. So what this is saying is that no matter what strategy the column player uses, if I use this mixed strategy P0, my payoff is always going to be at least as big as V. Right? And for the column player, similarly, this GQ0 gives me the payoff for the column player for all different possible strategies that the row player can use. And what this is saying is that the loss of the column player is going to be less than or equal to V no matter what the row player plays. Okay, hopefully you'll see that more clearly as we do some more examples. All right, let's look at this here. So here we have this game here, which in fact we looked at before. This was the store location game, and we discovered that it's better to locate both stores in town 1. So that would be row 1 is optimal strategy for the row player, column 1 is optimal strategy for the column player. Payoff is 50, and 50 is the saddle value. So in this case, since row 1 will always, row player will always play row 1, his strategy vector is 1, 0, representing the fact that he plays row 1 all of the time. Probability of playing row 1 is 1. Probability of playing row 2 is 0. Now, you can work out that if I take P0 times G, this gives me 50, 60. What does this represent? Well, 50 is the payoff if the row player uses this strategy and the column player chooses row 1. 60 is the payoff if the row player uses this strategy and the column player chooses column 2. I'm sorry, I think I said column 1 here and column 2 here. Now in either case the payoff is at least 50, so that satisfies the condition up here, P0 G greater than or equal to VE. All right. On the other hand, we do the same thing with the column player. Column player is always going to choose column 1. His strategy is 1, 0, representing always choosing column 1. His payoff is 50, 40, meaning that if the row player plays row 1, his payoff is 50. If the row player plays row 2, his payoff is 40. This is always less than or equal to 50. So we have it's less than or equal to this VF vector where V is 50. So this 50 satisfies these conditions up here. And we can see that the case where we do have a saddle value is a special case of this more general case. And it turns out that if we don't have a saddle value, we can still find P0 and Q0 in order to make this work. And we get kind of a saddle value from mixed strategies, but not from a so-called pure strategy where one of the strategies is chosen with probability 1. Okay, I'm going to stop here and we'll go on with the next video.